The title of this paper is Testing of a Green Monopropellant Integrated Propulsion System by Joe Carden, Tate Chappell, and Chris Day of VACCO Industries. The Integrated Propulsion System is a self-contained bolt-on propulsion subsystem specifically designed for small satellites. It features 4 flight-proven 1 Newton LMP103S thrusters produced by Bradford ECAPS. These thrusters are mounted in a double-canted position in order to provide pitch, yaw, and roll control when fired in pairs, and provide delta V when all 4 are fired simultaneously. Total impulse from this system is over 12 kilonewton seconds. A built-in shielded controller accepts 2 different power inputs in order to provide an interlock against accidental firing. Commands are accepted and health monitoring data is issued through an RS-422 data bus at a rate of 10 Hz. The system is specifically designed to be range safety friendly, utilizing the non-toxic LMP103S monopropellant, and also has 3 seals against either propellant or pressurant leakage. It utilizes a very benign helium pressurant, and the safe and arm circuit also provides additional protection. 3 of these flight systems are currently in production at VACCO Industries. The integrated propulsion system is designed for both safety and reliability. Low-pressure gaseous helium is continuously monitored by a pressure transducer, and all output of helium into the system is filtered through a 10-micron absolute filter that protects downstream components from potential contamination. 2 normally closed pressure control valves are arranged in series to provide series redundancy against leakage of helium into the propellant tank. A check valve prevents leakage of propellant from migrating up into the pressurization system. The propellant tank pressure is continuously monitored by 2 pressure transducers. These pressure transducers, along with the pressure control valves and controller, form a redundant electronic pressure regulator that's redundant both in terms of series redundancy against leakage, but also functional redundancy. Either pressure transducer can be used as feedback, and either pressure control valve can be used to pulse width modulate the flow of helium into the propellant tank. Overboard leakage through the thrusters of propellant is prevented by 3 valves in series. There are 2 valves that prevent flow into the distribution manifold, and each of the thrusters has a valve of its own, providing the 3rd interrupt. The system has a total impulse of over 12 kilonewton seconds and produces almost 4 newtons of axial thrust when used for delta V. The business end of the IPS is its 4 1 Newton thrusters. These thrusters are provided by our partner, Bradford ECAPS, and utilize LMP103S monopropellant. LMP103S is an ADN-based propellant that is non-toxic and non-carcinogenic. It's so safe it can be flown on commercial aircraft and can be fueled without the need for escape suits. It's 6% higher specific impulse than hydrazine and 24% higher density. It can be stored for 20 years, is insensitive to space radiation, air, or humidity, and enjoys a broad storage temperature range. The 1 Newton thrusters themselves are very well established. 58 of these have flown in space over the past 10 years. They're fully qualified for 60,000 pulses and 1.5 hours of continuous firing. They also enjoy a broad operating temperature range, and the exhaust gases are non-corrosive. Hundreds of these thrusters are in production or waiting for launch. The integrated propulsion system is a self-contained, complete propulsion system consisting of propellant and pressurant storage, as well as a feed system that includes valves and pressure sensors and filters, as well as thrusters and a controller. All of this is packaged in a robust, compact assembly, approximately the size of a basketball. This chart illustrates what's going on inside the IPS during the mission from beginning of life to end of life. As you can see, it's not a blowdown system where thrust changes with every firing. It's a pressure-regulated system. Even beyond that, since we utilize electronic pressure regulators, we can command any pressure at any time, and we can command a proportional thrust as a result. In addition, we monitor the helium storage pressure, which provides a direct measurement of how much helium is left and an indirect measure of how much propellant is left.
So this is the IPS, the Integrated Propulsion System test plan overview. We have 4 phases to this test plan for verifying flight hardware. We have an engineering model that is what we call a flat sat, tested at VACO, and we have this tested at customer facilities as well. Second, there is thruster acceptance testing using VACO valves by Bradford ECAPS in Sweden. Third, the IPS burst test at VACO, at VACO's California facility. And fourth, the IPS protoflight testing with thruster simulators at VACO's California facility. So for the flat set test plan, this includes visual inspection of the product, multimeter measurements, and then we start turning the system on and operating it. We perform a communications setup and then verify that telemetry is valid and correct. Then we start simulating thruster valve testing, and then heater and thermocouple testing. This includes heater temperature regulation and closed loop feedback of the catalyst bed heaters of the thruster using this flat sat simulator. And then lastly, pressure transducer testing. And so the IPS engineering model, this flat sat test article, features both a flight controller and software. It also includes valves, heaters, and sensors in this simulation. So there are sensors, heaters, closed loop capability with these heaters as well. So there are commandable temperature set points that you can command the system to, and it will internally closed loop regulate autonomously to the commanded temperature set point. So after all these tests have been performed, they have all been passed, and we have successfully validated the controller component selection and the circuitry, and the software is operating properly.
This shows the component level 1 Newton thruster acceptance test plan. This is conducted at Bradford ECAPS. They do an examination of product and check the thrust vector alignment. They also perform a catalyst heater thermal rise time check and vacuum to ensure not more than 30 minutes duration. Proof pressure is done with the nozzle plug. Functional testing pre-vibe occurs and includes external leakage and electrical checks. Random vibration test ensues at 2 different levels, followed by a post-radiographic inspection. Post-vibe functional test occurs again before proceeding into hot fire. Hot fire occurs at 3 different thrust levels, essentially 3 different inlet pressures. There is a 3-pulse 30-second firing done. There's 300 millisecond pulses done. And then specific to IPS, there is a 100 pulse, 100 millisecond test done at the high thrust level only. Following hot fire, a functional test is repeated. The test results are shown in this slide. You can see photos of the various tests in the upper left. The lower left has the vibe profiles, and the right side is showing example hot fire data. You can see thrust versus pulse number in the upper right. At the 3 different thrust levels, the red dots are showing the 100 millisecond pulse information. The hot fire data is then reduced for ISP that is shown in the lower right. All 3 IPS thruster sets have been delivered successfully, so we're 12 for 12. Burst testing occurs on a flight representative test article that's shown in the photo. The workmanship tests initially are the proof pressure test done at both the LMP and the pressure values. External leakage is a combined tankage test check. We then proceed into qualification, which is the pressure cycle testing at 50 cycles. That is a combined tankage volume as well. but at the higher pressure in MDP. Burst testing occurs at each LMP and pressure values. Then we proceed into a rupture margin test that is a combined volume test. Here you see the successful test results of the burst testing conducted. The workmanship checks turned out okay. The qualification pressure cycle passed the 50 cycles. There was a CT scan done afterwards to additionally verify. Burst test occurred on both sections as well. The upper right photo shows the item. There was no deformation observed and no leakage. Rupture margin test then ensued. That photo is in the lower right. You can see how it can deform, but it was at extremely high pressure. The item stayed together, and the ultimate 490% margin was applied to the higher helium pressure inside value. Proto-flight test plan involves examination of product. That's the dry mass. That would include thruster mass simulator since the thruster is not installed yet. Proof pressure testing, similar to before, occurs on the pressure inside at the higher pressure and the propellant side as well. Functional testing involves external leakage check to welded levels. That occurs at MDP. Individual valve leakage tests are done as well, also at MDP at the values indicated. Each of the 8 valves is operational and response tested, and we also do a regulation check using the pressure control valves that regulate pressure to the LMP tank. Pressure sensors are verified as well. There's 3 of them, 1 on the helium tank, 2 on the LMP, and power and telemetry verifications occur. An electrical functional test is done with the surrogate thruster heaters, and also the PWA heater is verified. Pressure regulation test then occurs with water in the LMP section of the tank. That is a pre-vibe test. Vibration testing happens with water still in the tank at 2 different levels as indicated using the thruster simulators. Following that, we do another wet functional test. A one-time throughput verification occurs. The subsequent units will not see that. And then the item is dried out and we perform the gas functional testing again. Thermal vac is next. 8.5 total cycles at those thermal plateaus indicated. That is well powered. Initial cycling does include a non-operational temperature dwells at greater values shown. Functional testing does occur at first and last cycles, and that includes controller cold and hot starts. Again, the controller is powered during all thermal excursions except for the non-operational temps. After TVAC, another gas functional test occurs, and we then proceed into thruster installation, which includes a thrust vector check and then actual heater sensor functional tests on the thrusters. We conclude with final examination of the product and packaging for shipment. The 3 IPS units being built are at various stages of assembly as the photos show. Proto-flight testing will happen afterwards. We have conducted a vibration fixture survey with mass simulator as photo right shows, and a variety of in-process tests have already occurred. Progress continues at VACO.
In conclusion, the IPS is a green monopropellant integrated propulsion system specifically designed for small satellites. It's a complete bolt-on propulsion system utilizing non-toxic, flight-proven LMP103S propellant. 4 1 N ECAPS thrusters provide pitch, yaw, roll, and delta V that is throttleable. It generates a total impulse greater than 12 kilonewton seconds and has an integral controller with health monitoring. Its structure is compact, robust, and all-welded titanium construction. Propellant and pressure and storage all are isolated with at least 3 interrupts against external leakage. The engineering model flatset testing has been completed and validated controller component selection, component circuitry, and software. All 12 1-Newton thrusters have already passed hot fire testing at Bradford ECAPS and have been delivered to VACCO for integration into the systems. IPS has passed the burst pressure test with 490% margin. All 3 flight systems will be protoflight tested.